everybody, and welcome back to IT Project Management. In this module, we are moving from project scope management and the work breakdown structure to one of the most important aspects in project management, project schedule management.
Here is what you will be able to do after completing this module. Once you are confident that all of your activity duration estimates are solid, it's time to figure out how to put these activities in a sequence that gets your project and product done in a minimum of time. This is what happens in a network diagram using precedence diagramming principles. Your schedule efforts culminate in the Gantt chart, which, when approved by the project sponsor, becomes the baseline against which all the actual work completion dates by the engineers in your team are being measured. To follow along, please open the work breakdown structure, that is the WBS, with the activity estimations that you have built previously in your favorite project management application. That can be Microsoft Project, Project Libre, or any other application that you may have been given to use in this course. This will help you understand better where we're going with this. To continue with this module, this is what you need. All your tasks organized in sensible hierarchies in a piece of project management software. This is your WBS. So let's recap. You're going into building the schedule with a well-defined WBS, and you know all the activities that need to happen to make your project successful and generate measurable organizational value for your client. So once you know the activities, here are more questions to consider. Who is going to perform the work? What is their skill level and availability? Can they work on my project full-time, or am I sharing them with other projects? Have I asked the team members really for their bottom-up estimate and added 10% reserve? And do I know how reliable their estimates are? And do I need to anticipate any extra time needed for communication? Those are a lot of balls in the air, aren't they, when it comes to building a schedule? So once you have captured and estimated all of the activities for your project, your next task is to determine how to arrange these activities to ensure that your project uses the shortest possible schedule. This means you'll have to figure out which tasks come first, which come next, which can run in parallel, and which ones can possibly be late without breaking the schedule. You are on your way to sequencing the activities. At this point, our goal is to develop a traditional project schedule. So let's finish the last step we still have to do, building our activity sequence. To sequence our activities, we will need to determine what comes first, what comes next, and what activities can run in parallel. To build our project schedule, we will first need to build a network diagram in which all sequenced activities are represented by boxes. These boxes are called nodes. Each box contains the title of an activity and its duration. Now we have to determine how these boxes should be connected. There are 4 ways to do this with the precedence diagramming method you're seeing here. The most common way of connecting 2 tasks is finish to start. This means that activity A must finish before activity B can start, so both activities are sequential. Another way of connecting the tasks is finish to finish. This means that activity B cannot finish until activity A is finished. If there is no other dependency between A and B, we get the best case scenario in which A and B can run in parallel and both finish at the same time. If there is a dependency between A and B, then B can always finish after A, and the longest duration will be A plus B, as you're seeing on the right side of the screen here. Two other ways of connecting activities are start to finish and start to start. If we're using start to finish, activity A must start before B can finish. In an ideal situation, this means that A and B finish at the same time, as long as A starts before B finishes. In the worst case, A starts after B finishes. Lastly, if we're using start to start, task B cannot start until A has started. This means that both tasks can start at the same time, best case, but worst case, A can start and even finish before B starts. Knowing how to make use of these four relationships is crucial when arranging tasks in an efficient schedule. Let's walk through an example. Take a look at the 10 activities in this table. Let's assume the letters in the activity column are WBS numbers, and our description is in the second column. But what really interests us is in the two columns to the right. Estimated duration in days, which you should have by now, given that you've talked to engineers and experts and have reviewed previous similar projects, and this is the big one, the predecessor column. That predecessor column contains the information we're after. It shows how our tasks are connected. Obviously, A is the first task and J the last one. We see that B follows A. But what about B? Define user requirements. In a waterfall approach, we have to have the requirements first before we can design web page layouts, set up a server, and estimate web traffic. But do we need to do these three tasks one after the other? No, we can do those at the same time. That is why they're all connected to B and run in parallel. Now let's look at task F. We can only test web pages and links if we have those web pages, and we can run them on a server. This means that F needs to follow both C and D. Pause the video here to read through the rest of the steps and, using the information in the predecessor column, figure out how the activities are connected. Then close your eyes for a moment and try to visualize all this as a graphic. If you have visualized this kind of graphic, you're doing great. We call this kind of graphic an activity on node network diagram. Here we see all the activities A through J from our example in little boxes, which we call nodes. The information from the predecessor column allows us to connect these nodes with the arrows or edges that you see here. On the top of these arrows, you see the values from the duration column. Now, this is a small network diagram. With a project that has hundreds of tasks, these network diagrams can get pretty complicated. And there's another complication too. If we want to get from A to J, which path should we take through the network? Are some paths shorter or longer? If so, which path is better? So let's calculate the possible paths for our network to see which is the longest and which is the shortest. For example, path 1, which leads us from A to B to C to F to H to J. If we add all the durations for the activities on that path, we get 18 days. We do the same thing with path 2 and 3 and 4 and 5. And then we realize that path 4, which leads us from A to B to D to G to I to J, takes 19 days. That is the longest path through our network. We call this the critical path, because if none of the tasks on it change their duration, that is the minimum of time we need to get the project completed. If any of the tasks on this critical path are late, the entire project will be late. What does this mean for you as the project manager? It means that as you get to finally doing the work on your project and building what you're being asked to build, these are the tasks that you'll need to monitor. Be ready, if any of these are late, to assign more people to these crucial tasks or to change your network by changing the predecessors for these tasks so that more of them can run in parallel. Whether you decide to add resources, which is called crashing the schedule, or rearrange the network, which is called fast tracking, as soon as the duration of the critical path is in danger, your project is about to be behind schedule. Not something you'll ever want to hear. And if that weren't the worst thing, how about this? If any of the other tasks take much longer than planned, this critical path can change too. You probably already guessed that babysitting the critical path is one of a project manager's most important jobs. And you'd be right. So as we just learned, the critical path can change if any of the other tasks run longer or start late. This means we need to know how much lateness or longerness we can tolerate before the critical path changes. This is called finding float. So now we need to do our math through the network. We start with activity A. We know it takes 2 days. So the earliest that activity A can start is day 0. Since it takes 2 days, it will end at the beginning of day 2. This is what we call the early finish, which follows the early start. So now let's look at task B. The earliest it can start is at the beginning of day 2. Since it takes 5 days, its earliest finish date is the beginning of day 7. On day 7 then, tasks C, D, and E can start. Task C takes 4 days, so finishes on day 11. Task D takes 3 days and finishes on day 10, and task E takes only 1 day, so finishes on day 8. So now we need to talk about task G. Since task G has both D and E as predecessor, it needs to wait until both are done. This means it cannot start any earlier than when D is finished on day 10. No matter whether task E has been sitting around there waiting for 2 days. Task G takes 3 days, so finishes on day 13. We've got something similar going on with task F. See how D ends on day 10, but C ends on day 11? This means F needs to wait until C is done to start. Given its duration of 4 days, it ends on day 15. Now H, you guessed it, has to wait until F is done on day 15 until it can start, no matter whether G has already been done for a while. However, I can start as soon as G is done on day 13. Since I takes 5 days, it ends on day 18, whereas H is shorter and takes only 2 days, but that doesn't matter. The last task in our network cannot start until, again, all its predecessors are finished. That is on day 18. Since our task J takes 1 day, our 10-step project here is done on day 19. And that is if all tasks start as planned. We call this relationship between the early starts and early finishes our forward pass. And we're already seeing that it won't matter if a few tasks don't finish on time. Well, where there's a forward pass, there's got to be a backward pass, right? In fact, we need both in order to calculate how much which activities can be late. This is called float, and very, very important for you as the project manager, because when it comes to having to react to problems during the implementation phase of the project, float can give you the flexibility to reassign people short term to take care of problems or risks that you couldn't foresee, and still your project won't be late. Hence, float for the win. All right, so backward pass. Here's how this works. In fact, it's pretty much the same as the forward pass, just in reverse. This also means that where in the forward pass we calculated the earliest start and finish dates for our tasks, during the backward pass we calculate the latest possible finish and start dates for our tasks. Going backwards then, we start from our last task J. The finish date for our project is day 19. So we take that early finish date as the late finish date and reverse our math. J takes 1 day, so 19 minus 1 is 18. Day 18 is the latest possible start date for task J. Let's move on to I and H because they feed into J. If task J's late start date is day 18, that is the late finish date for both I and H. Since I takes 5 days, that makes day 13 the late start date for task I. And with 2 days from day 18, that makes day 16 the late start date for task H. For task F, that means a late finish date of day 16. And because 16 minus 4 is 12, a late start date of day 12. For task G, its connection to task I means a late finish date of day 13 and a late start date of 13 minus 3, day 10. Day 10 then becomes the late finish for tasks D and E. And we do the math here, and day 12 becomes the late finish for task C. With the same logic as before reversed, any previous task must finish before the next task starts, so the late finish date for task B becomes day 7, which makes its late start day 2, and task A must complete on day 2 to be able to start on day 0. We have now calculated both the early and the late starts and the early and the late finishes for all tasks in our network. Why are we doing this again? Oh, right, float. Now we can determine if there is a difference for each task between its earliest possible start or finish date and its latest possible start or finish date. So all we have to do is subtract the early start or finish from the late start or finish. Let's take a closer look at tasks G and H to understand why this is important. Look at task H. Here the early start is on day 15, but the late start is on day 16. This means it doesn't really matter whether H starts on day 15 or on 16 and ends on day 17 or 18 because the following task J won't even start until day 18. That 1 day difference between early and late is what we call float. Task H has 1 day float. This means that the project will still end on time, even if task F, for example, comes in a day late. Yay, float! Now let's look at task G. See the difference? Exactly. For task G, there is no difference between late and early start or late and early finish. In other words, task G is not allowed to be late. If task G is late or runs longer than expected, task I will be late. That will cause task J to be late and break our project end date. Of course, we remember that task G is on our critical path. That's why its letter is red. Tasks on the critical path always have 0 days float. That, in fact, is the definition of the critical path. So now that you know how to build a network diagram from hand, let's see how professional project management software handles this. Here is a sample schedule in Microsoft Project. If you're looking at your open work breakdown structure in any kind of application, it will look very similar. You will most likely see all your tasks in the third column from the left, followed by the activity durations. If you haven't entered the activity durations in your project just yet, now is a good time to pause this video and do just that. Ignore the content of your start and end dates for now, and come back when you've gotten the durations column filled in. The next thing we need for our network diagram is the predecessors. Remember our 10-task project from earlier and how we saw that tasks C, D, and E followed B? As you can see in this Microsoft Project screen, the layout is really almost identical, only that here the predecessors are filled in based on the line number. So now is a good time to pause this video again and enter the predecessors for the task in your work breakdown structure. So now that you have both the activity durations and the predecessors entered, Take a look at the right side of your screen. Do you see how the horizontal bars span the number of days that you entered into the activity duration and how they are connected based on how you set the predecessors? Now, all that you'll need to do is enter one date into the first start date of your first task. If all tasks are connected, Microsoft Project and any other project management application will now calculate all your project dates and milestones. You just built your first Gantt chart. Congratulations! Wonder what this looks like in Project LIBRE? Almost exactly identical. In fact, this is by now a standard view in any project management application, no matter whether it's targeted towards waterfall management like Microsoft Project or towards a more agile methodology like Rike or any others. Are you curious how to get to an actual network diagram view? In Microsoft Project, you will want to click on the Tasks tab and then pull the first button on the ribbon down. This is where you will see network diagram in the built-in group. And here's the network diagram for the few little tasks that we just saw. Now, notice how some tasks are red and the others are blue? If you guessed that the red tasks are the critical path tasks, you'd be right. No more forward and backward passes to calculate. The software does that for you. Project LIBRE contains similar functionality.
Here's what we just walked through. We discussed how to develop a network diagram with the standard activity on node model and used precedence diagramming to establish connections between the activities. We learned how to use the forward and the backward paths to identify a project's critical path and calculate float on the tasks that are not on the critical path. Finally, we used project management software to capture what we did theoretically also at a practical level. You just built your first Gantt chart. That's great! Thank you for watching, and I look forward to seeing you in the next video.